Welcome to our materials science lecture on metal failures. Today, we will delve into the various types of metal failures and understand their underlying mechanisms. By the end of this class, you will be able to explain the conditions and mechanisms that lead to four major types of metal failures: nil ductility temp, fatigue failure, high temp creep, and stress corrosion. Let's start with low temperature ductile to brittle failure, also known as nil ductility transition. This type of failure was notably seen in the Titanic and Liberty ships, where steels had a transition temperature just below 25 degrees Celsius. To measure the fracture toughness of metals, we use specific tests that assess the energy required to create new surfaces. Brittle materials have low toughness, while ductile materials exhibit high toughness. The Charpy impact test helps predict the transition temperature of materials. It involves impact loading, which makes the material more brittle and decreases its toughness, measuring the energy absorbed in the process. The results of the Charpy impact test show that higher temperatures result in ductile behavior, while lower temperatures lead to brittle behavior in materials. Temperature significantly influences the impact energy of materials. FCC metals tend to be more ductile, while BCC metals and polymers become brittle at higher temperatures. Understanding this helps in determining the nil ductility transition temperature. Additives like carbon and manganese can shift the ductile to brittle transition temperature. Increasing carbon content in iron raises the transition temperature, while manganese lowers it. Cyclic loading can cause fatigue failure, which occurs in 3 steps: initiation, propagation, and failure. This type of failure is common in structures subjected to repeated stress. Fatigue failure can be analyzed through fractography, which shows the initiation, propagation, and rupture of cracks. Microstructural mechanisms play a crucial role in crack propagation under cyclic loads. Let's take a moment to review. A FCC metal exhibits a ductile to brittle transition. Increasing carbon content in iron raises the transition temperature, while manganese lowers it. Here are the answers to our inquiry. FCC metals do exhibit a ductile to brittle transition. Increasing carbon content in iron raises the transition temperature, while manganese lowers it. To predict fatigue failure, we use high cycle cyclic loading tests. These tests measure the range of stress and amplitude, helping us understand the stress at which failure occurs. The effect of materials on fatigue failure is depicted through SN curves. For FCC metals, fatigue limit exists, meaning infinite cycle lifetime if stress level is below the limit. For BCC metals, fatigue limit is finite. Another moment for inquiry. During fatigue failure, the absolute value of stress amplitude must be less than 0. Fatigue failures cause part failure even when maximum stress is less than the critical stress. Here are the answers. During fatigue failure, the absolute value of stress amplitude must be less than 0. Fatigue failures cause part failure even when maximum stress is less than the critical stress. To improve fatigue life, we can impose compressive surface stresses to suppress crack initiation and growth. Methods like shot peening and carburizing are effective, along with designing to minimize stress concentration. Let's recap our learning objectives. We have explained the conditions and mechanisms leading to 4 major types of metal failures: nil ductility temp, fatigue failure, high temp creep, and stress corrosion. Thank you for watching. Please like, share, and subscribe to this channel. Add a comment below the video to share your thoughts and learnings. What did you learn from the video? What topic would you like to explore further? This presentation contains copyrighted material used under the Fair Use Doctrine for educational, commentary, and research purposes. Links are provided in the video description to relevant resources.